I'm sharing already. Okay, do you see my screen here?
Yes.
Yes, okay, that your screen, my screen is nothing else but they have the homepage of our class. Now, I don't know why it shows like this, but in any case, what I decided to do, I will make this letters smaller and move them off so you have everything on online. But what I decided to do is we had a discussion on Monday about important dates to be able to show easily. And what I decided to do is to put here the important days that you need to keep in mind. So one is our midterm, which is going to be on Wednesday, March 17th. And then the next lecture that was going to happen on Friday, that day is a study day, so you know. And then the final is on Monday, May 3rd, from 8 a.m. until 10:30, excuse me, a.m., not p.m. I will fix all of this. But it's going to be both the midterm and the final will be on Zoom. Of course, our class is on Zoom, period, but I just wanted to confirm. And I mean, it's online. So it's going to be online. Both midterm and final will be open source, open everything. So the only thing is that you will have to work on this individually. And it will be nice to for you to have your video on. This is something that the university has requested that we do. Because it's not a take-home exam either. So in the other thing, I mean, it is a take-home, but not a take-home the old traditional way. So the other thing I wanted to say is that I may have a team question. We'll see how. I have not made up my mind yet. I just need to see how the teams work. I may have a team question towards the end of the exam, which means that I will have breakout rooms for you to get with your team members and spend some time discussing the question. But then each one of you will have to submit the question in your, I mean, individually, even if it may be a team question. We will see how that goes. I will tell you like about a week and a half, maybe a week before the midterm. I will tell you if that's the case. And then of course I will tell you if we do it for a midterm and works, then we may do it for the final. We'll see. I have to see how the teams work before I make that decision and see whether there are any teams that have problems. So with that, I also wanted to show you that today, I'm going down, I have updated here this homepage, and this week does not exist. We are in week 6, but module 5. I will correct that. So we are in module 5, and here is all of the information that I have available for today. You see that. Now, the other thing I wanted to tell you to help you, I went under files that you also see them. I went under files, and if you go under files and go into the uploaded media, I have put all of the files by week and module. So if you want to find anything, and I will keep doing this, you see I still have 2 more for module 5 to incorporate under week 6 module 5. But I will do this also for you to not be confused, because usually the way Canvas does it, it puts a long list of files that are very confusing even for me when I look at them. So I clean up. If I upload something twice, I remove the previous version. So it's easy for you to go to files and find what we have for this class. So with that, I would like to see if there are any questions you may have for me before we start the lecture for today. Or any suggestions?
I guess I have a question, Professor.
Yes, go ahead.
Regarding the material we were talking about last time, I'm pretty sure I understand it, but there's one thing that's kind of confusing me.
Tell me.
So in that one example where you showed the different points, and then you said the
Can I bring it over? Can I
sure.
bring this? Yes, thank you. 1 second. And then I will stop sharing here for a moment so I can share. It's from Monday's lecture, isn't it?
Yes, ma'am.
Yes, okay. So 1 second. I'm sharing screen, start. Okay, that is, okay, this is what we covered.
Okay, I think you need to scroll down a little bit. Yeah, that example, the green line, the green plot example.
Yes.
Okay, so you mentioned that you were talking about where the greatest change was, and
yes. Oh no, not the whether the greatest change, when the peak values of the electric field were. The greatest change happens, of course, where the line goes up, where it's not flat. All right. So the greatest change of phi happens at A, C, E, G, and I. But those, they tend to correspond to the highest value, to the peak values of the electric field, which is down here. And they're flipped because of the negative sign. Down here, 1, 0 at B, up here at C because of the negative sign. Otherwise, the derivative is negative. Around D is 0. Around E is negative, but peak value. So the positive and negative show direction rather, okay? So the peak values are around E, around F0, around G peak value, around H0, around I peak value, and around J0. And why is that? Because of this relationship. You see it here. Let me just take the pen here.
Oh, it's because, okay. I was getting confused because I kept forgetting about that negative sign. Okay.
Yes.
Okay, thank you.
Yes, there is a negative sign by definition, all right? These are conventions. And remember, we said the convention about the negative, the story, right? The historic reasons, rather, because all of these conventions have, they have no reason if scientifically speaking, but they are conventions. The negative sign came because people started thinking that the positive charges were responsible for the electric, I mean, the flow of positive charges was responsible for the current. But in reality, it's the flow on negative charges. And because they had already developed theories on the basis of that, they decided to have the negative convention to be able to then continue without having to alter everything that they had postulated up to that point. So it's a convention.
Okay.
Yeah.
Okay, that makes sense. Thank you.
You're welcome. Any other questions on this? Because practically we are going to continue with that. So last time where I left it, which is important to remember, is the following. That when you have a conductor and there is an electric field that either has been excited because of a nearby source or a faraway source, it does not matter. But an electric field around a perfect or a very good conductor will always be perpendicular in direction to the surface of the conductor. And we explained this by showing that there is no electric field on the conductor. We said there is no electric field on the conductor. Why is that? Because the currents are flowing freely. And because they are if there is at one point a time t equals 0, let's assume that we could be at time t equals 0 and observe what happens. The time t equals 0 when we turn on an electric field. And then we see all of the electrons moving under the influence of that electric field. And then they move and they go away. Usually, where do they go? To the furthest positions they could go, because obviously the electric field, which implies a source somewhere, exerts a force on the negative electrons, and that force moves the charges. And the charges will move either closest to the source as possible, or furthest from the source as possible, depending on whether the charges are positive or negative and how the electric field applies on them. So if the electric field is due to a positive charge, a positive source, then of course the electrons will try to go as close to this source as they can physically go. If the source is a negative charge, then the electrons will try to move as furthest away from this source as they can physically go. So all of the electrons, all of the charges, everything moves to the surface of the conductor, like the upper surface, physically the outmost point on the surface, which means inside the conductor, there are no charges, nothing, zero. And if there is no charge to move anywhere, that implies that there is zero field. All right, so there is no activity inside the conductor, zero. There is no movement of charges, there are no charges, there are nothing, so it's zero. And that's why you see here on the first figure that you have that. In that particular case, you see what happens? The metal before the electric field applies is neutral, has no charge. So all of the electrons are around their atoms, they are moving in orbits, or some free electrons scattered left and right, but and macroscopically, the sphere has no charge. But the moment this electric field applies here, which has this direction, that direction of the electric field is gonna force all of the negative charges to come, because obviously an electric field like that, what happens? Is created by a positive charge somewhere far away. All right, far away is a charge, is a positive and is far away and creates that electric field. So the negative electrons, because they see the direction of the electric field, they understand there's a positive charge somewhere far to down. All of the electrons, they will come as close to this positive charge as physically possible. So they will all crowd down with a non-uniform distribution, but they will all crowd down to the lower surface of the metal sphere. And all the positive charges will try to move as physically away as possible. So of course they cannot leave the surface of the metal. So they're all in the upper side of the sphere, and they're there, not uniformly distributed, as we will see. So that's what happens under an electric field. The charge is split, negative and positive, on the sphere, and they distribute accordingly, as we said. So here, this is an example, and I have to tell you, this example is rather, is not exactly calculated, if you like, or it's not out of the software, but it's more of a rendition of what will possibly happen if you have three metal surfaces. So for example, this is one here, metal. This is another metal surface. And this is a third one. So what is interesting here, there are a few interesting points we would like to make out of this. Let's look at the surfaces that have smooth, at the objects that have smooth surfaces. What happens is that there is a positive charge at the center. This charge here is here, it's located here. And then, of course, it creates a field with the directions that you see. The field goes from the positive charge to outwards. And then the field lines that are closest to the surfaces of these objects, of course, they will terminate on the objects at a perpendicular position. So even if it does not seem like this, the position here is perpendicular, and here and everywhere. The perpendicular positions. And also what is going to happen, all of the negative electrons will be crowded towards the positive charge. And all of the positive holes, the charges, or like the absence of electrons, or like all of these atoms that have been left with a positive charge, not exactly the atoms. I mean, you know, the electrons will move from these places down there. It's not like the atoms move. So all of the electrons that have moved freely here, the absence of them, the positive holes, will all be crowded on the other side of this and the farthest possible location. And they will show like this, where of course the field lines will start at perpendicular also directions to the surface. What is interesting here is something we said before. Look at this object, this one. This object has sharp edges. Now, this sharp edge on this side, this one, is the closest in distance to the charge. So there is going to be crowding of electrons around here because they would like to go as closest to this charge as possible. And then, of course, the other edge, which is there, also is going to attract many positive charges because they try to go as farthest from the positive charge as possible, and they are all crowded there. So what that tells you is that depending on the type of the surface of the object, the charges may distribute evenly or unevenly. And how evenly or unevenly they will distribute depends exactly on the shape of this surface of the object. So that is how you should think conceptually. This figure here is important, how conceptually you think of the distribution of charges under the influence of an electric field. Any questions about this before we move to a particular example?
Just to clarify,
Yes.
basically what you're saying is that like because of the specific shape, like it does actually depend on like what the shape is, whether or not the distribution of like the positive and negative charges will be equal.
Exactly. Exactly. Okay. It's exactly the way you said it. Perfect. So now let us look at an example here, which is a little more specific. So what we have here, and we'll solve a problem also as an example problem. So what you see here, this is a sphere. It's a sphere, the blue one, like this one. That's a sphere. And it's a metallic sphere. So that means that it has a thickness, all right? And inside that sphere, we have a negative charge, the red one here. And the negative charge, the sphere has a particular radius inside. And of course, the external radius is going to be bigger than the internal by an amount, the thickness rather. And the charge is located half the radius away from the center of the sphere. Okay, so now we are trying to draw the electric field lines that will be created because of the charge. So you see all of the electric field lines that come towards the charge is a negative charge, and that's why it's happening. So you see here, if I draw it, the picture, so it's all of these lines here. So practically I can use this one to show you. So this line here, it goes towards the charge, it starts at the charge, and then it ends perpendicularly to the surface, to the internal surface of the sphere. And because the charge is negative, it's all the positive charges that will come to distribute on the internal surface of the sphere here. You see that? This is the internal surface of the sphere. All of these positive charges will come and distribute there. But what happens? Because the charge, negative charge that creates this electric field is asymmetrically placed inside the sphere, so it's not at the center of the sphere, it's somewhere off the center, then it's closer to one side of the sphere and farther away from the other side, which means now all of the positive charges have come to mostly concentrate here. So as you go, see there is a variable distribution of the charges here. There are more charges at the close to around the place where the negative charge is closer, and there are fewer charges on the other side, as you can see. So practically, you see here how the distribution qualitatively develops. Now, what is the other thing that you have to keep in mind? Let's look at this sphere, but let's try to see what happens inside the sphere. So what happens inside the sphere? All of the free electrons that could move, they move, of course, away from the charge. So all of the free electrons are concentrated on the outer surface of the sphere. All right? All of the positive charges concentrate on the inner surface of the sphere. So what do we have inside the sphere? Inside the sphere, there are no charges. You remember we said that there is no charge inside the sphere, which means what? That inside the sphere, how much is the electric field here? At one point inside the sphere, how much is the electric field?
0.
0. Okay, what does that mean? This is very interesting what it means, and I will give you an example because otherwise it will be difficult to comprehend that. So let's assume that we have 2 rooms, and I say, and half of us become a negative charge, and half of the other students become a positive charge, so equal numbers. So then all of the negative charges will go into one room. All of us that are a negative charge will go to one room. And then all of the other positive charges will go to the other room, and we'll close the door. And then we will not be able to see or hear. Then what happens? If you are in 2 separate rooms without having any information about the outside, then you distribute any way you want. If, for example, it's a big room, then we can distribute far away. If it's a small room, then we're going to distribute more closely. And then if the room is cylindrical, then we can distribute evenly, especially now that, say, under the COVID, we have to be 6 feet apart, all right? So outside, however, in the other room may be totally different. So what the other students do, we don't know even. And the other students don't know what we do. So in reality, they will do whatever the other room suggests. You know, the shape of the room will encourage them to do. So that's what happens with charges. The positive charges inside see nothing from the negative charges outside. So the way the positive charges distribute inside is totally different. And it only depends on what happens inside the sphere from the charges that distribute on the outside surface. And it only depends what happens to the outside of the sphere. Okay, so here is the thing that sometimes students find difficult to comprehend. That the distribution of the charges inside the sphere is totally different from the distribution of the charges outside of the sphere. So inside the sphere, because the charges see the negative charge that is generated, it's they distribute unevenly. But outside of the sphere, that they only see practically the charges don't see anything to encourage, they don't see other charges, they don't see anything else. So they distribute evenly. And that's usually what happens, all right? Because the charges have the same sign, they will try to go away from each other as much as possible. So eventually they distribute evenly because they have the same sign. They will be forces that will force them apart, but they will distribute evenly. But inside, because of the influence of the negative charge inside the sphere, the positive charges crowd at a place which is the closest to the negative charge that created the field, this one. So when we solve for the problem inside the sphere, we forget the outside and we solve a problem that shows that we have this charge here and this metallic surface with all of the positive charges. We solve that problem. But when we are to look at the outside, we don't care about what happens in the inside. The total number of negative electrons that will accumulate on the outside will be equivalent to having this negative charge at the center of the sphere. So you can solve the problem at the outside as if that negative charge was centered at the center of the sphere. And that's how the field looks outside. So that is fundamental in trying to understand it. There is a second derivative to that, which in fact was the most critical thing that drove us into analyzing this problem. In the beginning, people would think that, you put a sphere around a charge and you isolate it. But that's not true. If the sphere is freestanding and is not connected to anything, like electrically speaking, then the outside field is equally strong. It's not like that you have eliminated. So what do we need to do to be able to eliminate the outside field? We have to ground the outside of the metal sphere. Not any other point, just the outside of the metal sphere has to be grounded. And why is that? Because if we ground the outside of the metal sphere, and then consider that the ground is like a sink, an infinite sink of charge, all of the electrons will flow from the outer surface of the sphere into the sink, into the ground. And in that case, it's going to be the sphere is going to be with this grounding, the sphere, let me just do it here. The sphere is going to be like, it's going to have the charge here at the center. And it's going to have all of the positive charges distributed as it shows here unevenly. And the outside of the sphere is going to be 0. And the field outside of the sphere is going to be 0. So practically, the only place where there are going to be field lines is going to be here. There. As it is in the book, in the example rather. Symmetrically, obviously, because there is this symmetry, this is a sphere. And that's why we always shield every wire that we have out there. There is a ground. Otherwise, if you don't ground your instruments that you try to measure, your instruments you're using, then you're going to have fields everywhere. And of course, this is not going to work, all right? The instrument you're trying to use to measure is going to give you a lot of noise or like incorrect data, or if you try to use it, it's not going to work. So this is the fundamental in the shield. Now here, it shows is an example that I have incorporated that shows how you solve the problem. And we are going to spend time a little bit doing that. And let me see. And I have another example. Okay, this one is in fact the full example here. And I will show you another one that I have in another document that is also included. Same thing. So for example, let's try now to understand, and let me add a page here, how we would solve this problem. We have now, for simplicity in the solution, we have the charge centered in a way that is preserves the spherical symmetry. So the charge, which is now a positive charge, plus Q here. The charge is here. Let me see, here. Okay, does not show. The charge is here at the center. And the sphere is the blue one. And then the other circles that you see is what I'm using to really define, to be able to solve for the field internally and externally. All right, so how we are doing that? Using Gauss's law, if you remember. So let's try to solve the field inside the sphere. How do we solve the field inside the sphere? We take any, so let's say, I will write it here so you can follow. So this is the charge. It's a positive charge. And this is the sphere. Okay. And then I know that this is plus Q. And then plus Q creates what kind of a field without the metal? So the metal here, this is the sphere. Let me make it. Oops, style. Okay, this is the sphere. And the sphere inside, because this is a positive, is going to have all of the negative electrons. Let me put the negative electrons on the surface here. And they're going to be evenly distributed because of the symmetry. All right. In fact, unless there is an external force that brings them together, because they have the same sign, they will tend to be as far from each other as possible. So that leads to an even distribution. Okay, so now what do we do? If we're going to find the field inside the sphere, then we define a surface. And in fact, I have mentioned it here somewhere, and I want to show it to you. Oh, it's called the Gaussian surface. You see that is mentioned a lot of times. I have not used that name here, but you will see it sometimes. So why is it called a Gaussian surface? Because we start with Gauss's law. And what does Gauss's law say? That the divergence of D equals what? Who is going to tell me? Any response? Can you hear me?
Is it Q?
Q. Okay. I just want to make sure that you guys hear me once in a while. That's what I'm going to ask questions also. Otherwise, it feels very lonely on my end. It's like I'm talking to myself. So you take the Gauss's law. So every surface we define, and you remember when we are to solve a problem using Gauss's law, where the Q is distributed, at one, it's like localized at one point. This is a point charge. Usually we use the point charge. We use the capital Q charge. Okay, you can see that it looks like N here, but charge. We use the capital Q for point charge. Okay, so you remember that. So it's that point charge. What do? We take then a surface, we define a surface around it, which is like a sphere. and has a distance from it, which is r. All right. Then what do? We apply the divergence theorem on this. What does the divergence theorem say? As we know, that the integral of this on a volume around the sphere, and that's a spherical volume, we selected a spherical volume. That's the surface of this volume is called the Gaussian surface. All right, Gaussian surface, since you saw that, is because Gauss, when he established his law and started putting the divergence theorem, he defined those surfaces. So that's a Gaussian surface. All of these individuals who developed the laws of electromagnetics were also not physicists, but also mathematicians. So they were, at the time, everybody was a physicist, a mathematician, and everything else. That was in the 1800s. Okay, so Gaussian surface. And that tells us that this gives us the volume integral, of course, of a charge density dV, but we know that we only have a point charge, so it's Q. Okay, and this is, of course, the charge inside the volume that is defined by this Gaussian surface. And then what does the divergence theorem say? That the surface integral on this surface S, and that's the normal vector to the surface integral of d dot ds equals Q, and the surface integral of that, since d, this is symmetric, and d is we said that the electric field is going to look like that out of Q, so it's going to be perpendicular to every sphere that centers around Q. So if this is d, then d is going to be, it's going to have a component along the radial direction, that ds. All right, and is the direction of the surface. So this gives 1, and that is equal to Q. And therefore, this integral gives us, because dr is the same everywhere on the Gaussian surface, gives us dr 2 pi r squared equals Q. So practically that gives us the d equals Q over 2 pi r squared, and is along that direction. Okay, that's what we found. So the electric field inside the sphere is going to be Q over 4 pi, excuse me, did I say 2? Sorry. Somebody has to correct me. 4 pi for the sphere. 2 pi r is for the circle. 4 pi. 4 pi. Epsilon naught, assuming that it's in free space, r squared, a sub r. Okay, that's what we found. So inside the sphere is going to look like this. And how is it going to look outside of the sphere? Okay, so inside the sphere looks like this, and that's what you have here. All right, you see in this 6 and 7. And then because of that, you have this relationship that we found. What happens outside of the sphere? Outside of the sphere, when we get with shielding, everything goes to all of what happens rather, all of the electrons flow into the ground. Or you can say usually, or in this particular case, if you have electrons outside, they will flow to the ground. If you have positive charges outside, because see what happens here is a positive charge inside Q are all of the electrons that collect in the inside surface, all of the electrons here, and then all positive charges here. So since there are positive charges here, and positive charges do not necessarily move, they just show a lack of electron, then will be a flow of free electrons from this sink, which is an infinite sink, has an infinite number of free charges. Those electrons, they will flow and then will neutralize all of the positive charges. So practically, outside of this sphere, the electric field is zero. That's what that shows. So here you have some additional examples from previous thing, but I wanted, before we go to these additional examples, I wanted to go to an example here that I would like to discuss with you, and then you can see the solution. It's the same problem, but instead of a sphere, I have a cylinder. Assume that instead of a sphere, I had a cylinder, and at the center of the cylinder, I have a line charge. And the cylinder is thick, so it has an internal radius, rho sub I, so we are in cylindrical coordinates, an external radius, rho sub E, and it's a line charge, which is charge per, so in coulombs per centimeter, per unit length, whatever. I gave you a number in this particular case. And now we want to find the field inside in the cylinder and outside when the cylinder is not grounded. Okay, so here is what we know ahead of time. We know this. We know, first of all, because the cylinder has a cylindrical symmetry and the charge is at the center. That means that all of the fields that will be created will be cylindrically symmetric. We know that. Then, and therefore, the field is going to have a direction. Wherever there is a field, the direction is going to be along the radius. So both in the we'll start with the inside. We know that the electric field inside the cylinder is zero for the reasons we discussed previously. And we know that since the cylinder is not grounded, we know that all of the positive charges will be outside of the surface of the cylinder, which means that all of the positive charges will be responsible for an electric field outside. And because we have here in the center, we start with the center, a line charge, we have concluded from previous examples that the electric field that is generated by an infinite line charge or an infinite charge wire, if you like, is varied as 1 over the distance from the line charge, which is in this particular case, the radius rho of the internal cylinder. So inside the cylinder, in this area, the field is given by that, and we have proven this. Inside the cylinder. In the cylinder, in the metal of the cylinder, this is zero, of course. External to the cylinder, how do we find the electric field? By applying Gauss's law. And I believe we did that for a sphere previously, when we did charged spheres. If you remember, we saw how to develop that, but we start, where do we start? We start with Gauss's law. In this particular case, why do I have Q? because all of the charges are distributed on the surface. Therefore, I don't have a point charge, but I have a surface charge distribution. All right. And what I do, since especially is infinite long, then practically I'm looking at one cross section. So instead of a surface, which is like the surface of the cylinder, here my charge distribution is going to be a line charge distribution, which is going to be along the perimeter or the periphery of the external circle, which is the cross section of the cylinder. So since we have an infinite cylinder, we are looking at the cross section of it, and Q sub L will be the line charge distribution along this cross section. Okay, how much is this line charge distribution? It is all cumulative, equal to this Q sub L. All right, all cumulative is that. But so I don't want to confuse you here. So let me still keep it as Q sub S. So you remember that is a surface charge, but we see now only one cross section. I mean, the cylinder practically would go like this. All right, that's how it would go for infinite dimension. And then we apply the divergence theorem here. And that's, of course, along all the surface of the cylinder. So in fact, so that looks like this. And also, this would look like this. And because it's an infinite cylinder, then practically this is going to go to the surface of the cylinder, but let me do it then intermediately. And this is going to practically give us Q sub L. And then, because the cylinder now is infinite, this is going to be a line integral of d dot dl on this outside circle, which shows the outside cross section of the cylinder, and that's Q sub L. And how much is since the charge distributes evenly along that, and then for D is going to be cylindrically symmetric, that implies that D sub rho times 2 pi rho sub E, which is the external surface, is going to be Q sub L, which implies that E sub rho is going to be 1 over Q sub L over 2 pi epsilon naught rho sub E if we are right on the surface, or rho if we are on any other surface further away. All right, so practically, if we want to be on the surface further away, we're going to have that rho here. And that gives you exactly what you found here. Now, because I have used a general medium, you see here, that has epsilon sub 3, instead of epsilon naught that I put here, is going to be epsilon sub 3, just for a general case where the dielectric outside is different than air. And that's exactly what we found here. So when you ground it, of course, there is 0 outside. And that's what you see here. So that's an example that I would like you to go through when you read that, and that has to do with shielding and grounding. All right, so that is an important example to go through because it really gives you now the case of the sphere from the lecture and the case of the cylinder from this example. These all examples are on your notes. The other thing that I want to show you is that I have included a problem here, which is not from today's lecture, but I decided I will give you also some solved problems for you to read from previous material so we can bring back some concepts that we've seen before. We have done the electric field that is excited by one line charge. So you have one line charge here along this line. And then we have found the field. But now I consider to have two line charges, one along the z direction, one along the y direction. And here I want to find the electric field at point A, all right, which is I give somehow point y, and it's a point given like has a y coordinate and a z coordinate. And here it shows how to solve the problem by superposition. So this is I did it as a homework some time ago, but here is what I would like you to see the solution of this problem, just so you remember, like an application that we've done in the past lectures. And I will always try to have problems like that in hopefully in every lecture to be able for you to do some review as you go through. So with that, I wanted to tell you that I also want to give you for today, let me see, 1 second. Here. Okay. This is not the first time. Okay, well, I will add, let me go. I will give you, so let me say, check today, because for some reason this one does not, unless I try to do another one once more. Let me try to do this. Yeah. Okay, that's it, what it is. I would like to give you one more exercise. Go here. Here. And in fact, since we have not done the capacitor, I will not give you an exercise today. This is going to be, I will give you a quiz on Friday. So no exercise today. I'm not going to give you another exercise, but I would like to see how many they've done the potential. Now, good. It seems like most of you got it. You see what I see here? This one. However, look at this. Out of 72 students, 12 students have not taken the opportunity to do this exam, this exercise. So these 12 students, I need to see, I will start looking at the grades. I mean, I don't know why they would not even try to do the exercise. If you don't try to do the exercise, you don't even get 15 points out of it. Somehow, I don't know why the students, and I give it for such a long time, all right? But I will need to find out who is not doing those exercises, and I need to come and speak with people individually. So I will unassign it, and I will speak with the students to see why they cannot do the exercise, what the problem may be. Okay, so I will see you. Do you have any questions before we go away from this lecture?
I actually have a question. Oh, sorry.
Oh, you go ahead. Sorry.
Yeah, I have a question regarding the spheres with the charge in the center of them. So regarding those examples, I guess I have a couple of questions. First of all, so suppose that charge isn't just sitting in the middle of those spheres or cylinders. Suppose it's actually moving around.
It's moving, or is like stationary but not at the center?
Well, no, moving. So I know we did an example where it wasn't off center, but yeah, suppose the charge is moving about inside that cylinder. Yes. Would the charges on the outside stay at the same distribution?
Yes. Is it
Okay.
not interesting? Yes. I mean, whatever happens, unless the charge is moving with a velocity, which means that's different. If the
Oh,
charge,
that's what I was asking.
yeah, if the charge is moving with a velocity, so here's what happens when you have, and we're gonna go into that on Monday. When you have one steady charge, the charge, it creates only an electric field. When you have a moving charge with a constant velocity, it only creates a magnetic field. Interesting, all right? So it creates only a magnetic field if it's moving with a constant velocity because it creates a current. If the
Right.
charge is moving, but it accelerates also, positive or negatively, then it creates an electromagnetic field. So if the charge is changing position, but not necessarily moving, you know, like a current, then if it only changes position, then the outside is going to remain constant. But if it moves with a constant velocity, then practically creates a current and then creates a magnetic field. And then we have to see what happens when you have a magnetic field.
Okay. And
All
I
right.
guess that leads into my other question. When you ground the outside of the sphere,
Yes.
doesn't that create moving charges, and therefore wouldn't there be a magnetic field around it?
No, because what happens is instantaneously. So all of these electrons move instantaneously. I don't know how to, maybe at time t equals 0, something happens, but we don't measure it. It happens so fast because those charges move with the velocity of light.
Okay. Okay.
All right. So you don't
Thank you.
see it practically. It does not make any impact on everything that we experience in life here on Earth, rather. Yeah.
Okay. That answered my question. Thank you.
All right. You're welcome. The other person who had a question?
Yes. So
The one.
for computing the electric field both inside and outside of the metal,
Yeah.
I mean in the air. Can
Yes.
we just use Gauss's law with the this law that states the total electric flux through any enclosed surface is equal to the total charge enclosed by that
Sure,
surface?
that's what you do. That's how we do it. That's how we do
So
it.
the
here.
outside, it wouldn't matter what the metal enclosing the charge look like the outside would just be the same every
Well,
time because
yes. So here's what happens. It is true, exactly, that if say the outside looked like this, if I understand your question, let's assume that you have a metal like this. Oops. All right. And you have a charge. Is that what you're saying? You have a charge here. So you're going to have all of the negative charges here, all of the positive charges there. The bottom line is there, yes, that if you go far enough from this, what you see here, if you go far enough from this surface that's arbitrary, what you see here is exactly what you said. It's like the field that it would be generated by this one, all right? Exactly, outside. But if you don't go that far away, so for example, what happens that if you come close to the surface, that is not true. See? Because if you come close to the surface, this point is closer to this than this point. So the value of the field here and there would not be what you would normally find between here and there. So if your surface is arbitrary, you have to be far enough away so you don't see the variations of the surface as much. And so the field that you will see will be more like the one from the charts. That's what I'm saying.
Ah, okay. Yeah.
Yeah.
I was assuming the arbitrary surface would be regular.
The regular is fine, but the reason I'm saying that is because your cylinder may be like this, might be a waveguide. You may have a waveguide, which is nothing else but a rectangular hollow tube, and then you have a charge here. Now, what happens here, if the waveguide is not grounded, which is a bad deal, all right? If you don't ground your waveguides, if you go to the lab, then you measure like noise. You don't measure anything because you have electric fields everywhere. So you normally ground all of these things, and you ground them through the flanges you are using to connect them. But in any case, so let's assume that you have this charge and it's positive for a moment. Let's assume it's positive. So the lines go like this. And the lines will go more. You remember what I said, that the negative charges like to go into the corners. There is something to be said, which we cannot explain theoretically now. We don't have the, we are not gonna do this problem right now in this class, but it's gonna go like that anyways, the field. And then the outside, the positive charges will also go somewhere here. They like the corners very much. And then so outside is gonna look, eventually if you go far away, it's gonna look like this, as if the charge was all far away from the waveguide. But if you were to go closer, the lines will look like this more. They will deform, all right? So if you go closer here, the lines, the field, if you are close to the waveguide, is not gonna look like what it will look out here, which is gonna be more like the field of a cube, of a charge, of a point charge. So they will look like this. They will look deformed because of the surface. So you have to go far enough from an irregular surface to be able to see what we are saying, the field of a cube, of a charge, regardless of the surface of the metal around it.
Okay. So if computing, like if we're not assuming we're going far away from the metal, then
Yes.
we still have to take into account of the shape of the metal, basically.
Yes, exactly. So
Okay.
practically you would have to solve the problem considering you would have to solve what we call a boundary value problem. And you would have to do it inside and outside. Boundary value problems mean, we will see them later. When you have a differential equation, we are gonna go, like instead of using Gauss's law, we'll go to the potential and create a differential equation for the potential. And then the boundary conditions say that the potential on the metal is equal in inside and outside, it's equal everywhere. So you have to apply a second order differential equation for potential, where the potential has a particular boundary condition. And then you will have to find the solution, which is going to be the most accurate way of finding the potential, and then of course the electric field. So it does change, of course, because the boundaries. So why did I mention that? When we say we solve a boundary condition problem, which is all the problem in electromagnetics, that implies that
Professor, I don't think we can hear you.